Welcome to Lesson 6F, Evaporation Multicomponent. We're going to talk about evaporation of a multi-component liquid. This is actually valid with or without wind. We're going to also introduce Henry's law and Raoult's law, and I'll show you an example. We'll look at two cases, single film evaporation and two film evaporation. Single film evaporation is the easier one to understand. We have evaporation occurring because we have this volatile liquid, and then there's a partial pressure curve here at the interface. It's PJI, and then it goes up to PJ infinity, which is roughly 0 in the boundary layer far above the surface. Meanwhile, we have a velocity boundary layer with some free stream speed U infinity. For a single film evaporation, we're saying that this xj here is a constant. So this liquid mixture is well mixed, so we assume there's a lot of currents around and mixing everything up. So there's one film in the air, but there's no film in the liquid because it's all just a constant. So we have a molar flux that's of the species going from the liquid due to evaporation into the air. And so you would have that same molar flux or mass flux. We like to speak in terms of m dot j. So you also have an m dot j. Everything is the same as the previous problem, except PJI at the interface is now not equal to PVJ. Other than this, we can say that all else is identical to the previous problem.
Why is PJI not equal to PVJ?
Because this xj is not 1. If you recall, xj is the mole fraction in the liquid, so it's equal to nj over nt. And here we would have j is the chemical, the VOC, and that would be j equal 2. J equal 1 would be the water. You could have chemicals dissolved in other liquids, but we're only going to talk about water here. We'll use J as the VOC. And xj here is a mole fraction, just like yj was nj over nt for a gas. Xj is greater than or equal to 0 and less than or equal to 1 by definition, just like any mole fraction. For a pure liquid, xj would equal 1, but we have a mixture, so it'll be somewhere between 0 and 1. Just like there is a PV or a PSAT for vapors. In other words, there's a maximum concentration for vapors in air, and that would be the saturation. There's also a maximum saturated xj for most VOCs, and most chemicals actually. You may remember this from chemistry class. If you take salt or sugar or some other chemical and you try to keep dissolving more and more of it in water, you get to a point where the water just cannot absorb any more of it, and so it'll settle out. So there's a maximum solubility. So the xj max is going to be less than 1, of course, but it'll be some value, so all xj's will be less than or equal to xj max. The PJI here is not equal to PVJ, so how do we calculate that? That's going to be the question now. So let me ask a couple questions here and answers. How to solve for m dot j, which is our evaporation rate that we're interested in. The answer for single film evaporation is exactly the same as previously where we did a pure liquid, except PJI does not equal PVJ. It would equal PVJ if a pure liquid, and it would be PJI is less than PVJ when xj is less than 1. So it's really a matter of finding this as a function of xj, and then we can solve the problem exactly the way we did before. The next question is how to find or estimate PJI. Well, it turns out that PJI equal a function of xj and temperature. We're going to assume we're always at atmospheric pressure. That will make a little bit of difference too. So we will use experiments to find this. So here's how you set up the experiment. You would have a container, and you have the so-called frictionless piston, like we always like to define in thermodynamics. So this piston goes up and down freely. We have P atmosphere up here. Just call that P or PATM. That's atmospheric pressure. Assume that's SATP type conditions. Let's pick some temperature. It doesn't have to be SATP temperature, but some temperature. We keep that constant. Isothermal. This is the liquid mixture xj less than 1. It's water plus species J, the chemical we're interested in. And we're assuming, this is a big assumption here for these single film cases, that this is well mixed. If I take the concentration there or there or there or right at the interface, it's the same everywhere. And then up here we have air plus species J vapors. So this is a gas mixture, and we assume always ideal gas at Y, J, and PJ. And PJ equal PJI everywhere here too, because this is also well mixed in the air. So PJI is the partial pressure at the interface. It's also the partial pressure everywhere. So all you have to do is measure PJ. After this thing has come to equilibrium, it's saturated the air as much as it can for that particular XJ. When you plot these, you'll plot PJI versus XJ at various temperatures. And these will then be called equilibrium because you've let it go to equilibrium. And they're isotherms, meaning constant temperature. So these are equilibrium isotherms. And when you do that, you will get a plot of PJ versus XJ. When you conduct this experiment at some temperature, you will get something like this. So here's XJ, and here's PJI, or just PJ because it's well mixed, both starting at 0. And this goes to some max XJ. It's not necessarily 1, although it could be, but it's some mixture of XJ. The maximum possible is 1, but it might be less than that because of the solubility limits. Typically, we get a curve that looks something like this. We see that PJI increases with XJ, and this is at some temperature. If we go to a higher temperature, everything shifts up, but if you go to a lower temperature, it goes lower like that, because temperature tends to make things evaporate more quickly. So this is the curve that we're going to look at, this one in the middle here at some temperature. Now the question is, if you have this as a table or something, you can pick it off of the table or off the plot. But what we're going to do is concentrate on a couple regions here. The first region will be in this region where you can see that we're almost linear for very small xj. And then we have another region up here where the slope again is fairly constant. So this would be high. I put high in quotes because again, it might not be 0.99. It might be much smaller than that depending on the solubility. But this is for high xj. And you see that there's slopes. So we can make approximations based on these slopes. This slope at the high concentrations is PVJ. And this slope at low concentrations is H prime, which is Henry's constant. There's two approximations we're going to talk about, Henry's law and Raoult's law. These are approximations. Based on what I just showed you on this curve, if you have very small xj, this will be Henry's law. I'll talk about that one first. And what Henry's law says is that if xj is small, much less than 1, then pji is approximately h prime times xj, where h prime is this slope of the curve near 0, or at 0 actually, and where h prime is called Henry's law constant. So it's just a linear approximation. We can find Henry's law constants in Appendix 8.9 of our textbook. This is the case that we'll most often use. And then you have Raoult's law. If xj is large, again, close to its solubility limit, then this one's even easier. Pji is approximately pvj times xj. So no new constants there. This is just using PVJ, which we know how to look up. That depends on temperature, of course. So if you have a temperature other than 20 or 25 degrees C, you have to interpolate, as I showed you before. When we have very small xj, we're taking this green dashed line here, a linear slope. So we're just in this little region. If we have a very high xj, we're taking the slope as PVJ instead of H prime. If you're somewhere in the middle in this range that neither Henry nor Raoult apply, you're kind of stuck. You got to go to some tables or figures plots like this to be able to find that. Now, if you want a little way to remember this, Henry, H comes before R in the alphabet. So Henry is the lower one, Raoult is the higher one. Henry's law applies here. Raoult's law applies here. Another comment, these so-called equilibrium isotherms can have other shapes. I had drawn this. You can also have something that looks like this. This would be the typical case, and you can see that H prime is greater than PVJ because this slope is bigger than this slope. But for this other case, you have the opposite. This slope is smaller than this slope, so H prime is smaller than PVJ. So that's just a different kind of fluid. And then you can also get some cases where it looks like that. In all these cases, Raoult and Henry still apply, but you can have this kind of fluid, this kind of fluid, or this kind of fluid. They have different shapes. So I'll do a quick example problem for you. Suppose we have ammonia dissolved in water. It's evaporating into air, so it's multi-component liquid. The mole fraction of the ammonia in the liquid mixture is very small, 3.5 times 10 to the minus 6. The liquid mixture is well mixed, so this is a single film. The air above the surface is at SATP. Estimate the partial pressure of ammonia vapors of the air right at the liquid surface. The first thing we need to do is obtain H prime from Appendix A9. I'm showing this because there's always problems with the way this is listed with 10 to the 7th. A lot of books do this, and we did this in our book. We don't like to keep typing out that 10 to the 7th for each entry, so we put that in the title. So if you take ammonia, Henry's law constant, H prime, is 0.03 times 10 to the 7th from here, and the units are Newton per meter squared. So it's the same units as pressure, as it must be by Henry's law, so that you can get your PJI in units of pressure. Once we have that, we then determine that, as I've already said, this is very small. 3.5 times 10 to the minus 6 is our XJ. And since XJ is very small, no question about that in this case, 10 to the minus 6th, Henry's law applies. And so PJI is equal to H prime XJ, and the rest is just plugging in numbers and watching units, as is always the case. They only give it to 1 digit, but I'll give my answer to 3 digits here just for continuity's sake for what we normally do. 0.03 times 10 to the 7th Newton per meter squared times XJ, which is 3.5 times 10 to the minus 6th. There's no units to that. It's non-dimensional, just moles of species per moles of water. We have our answer then in pascals or Newton per meter squared of 1.05. So PJI is approximately 1.0 Newton per meter squared. I can't justify more significant digits than that. I don't want to spend too much time on the next topic, two-film evaporation, but I just wanted to say that in this case, we have 2 films. We have also a liquid film or boundary layer as well as the one on top. So we have 2 films. We still have evaporation. And diffusion is always from high concentration to low concentration. Here we have a high concentration. Here we have a low concentration. That's why we get diffusion or mass moving from below to above, moving to the surface. The problem is to find PJI. The key here is that m dot j is the same in the liquid and the air, and sometimes you need to do some iteration to figure all that out. The liquid film shape, its extent and how big it is and its slope and all that, depends also on dj water, which is also in Appendix A.9. We haven't talked about that yet, but if you look, say, at our ammonia, we have a water diffusion coefficient. Multiply this by 10 to the minus 9 in meters squared per second. This is kind of like dJ air, which is this middle column, but this is for water. And therefore, how to solve, again, identical to previous, except you need to somehow find PJI. Once you have PJI, if you cover up the liquid, so you're looking at the surface and this film, the boundary layer is up in the air, it's identical to the previous solutions if we know PJI. Now, to find PJI involves a lot of algebra, and it involves some iteration sometimes. So PJI is not equal to PVJ. Henry or Raoult's law don't necessarily work everywhere down there. We can't just use that easily because XJ is not a constant. It will work at the interface. And so it turns out that PJI is a function of XJI, and that you can use Henry's law, etc. But we don't know what XJI is. So we're going to have to iterate to find XJI, and PJI is proportional to that. That's all I'm going to say. Just see example in the text, and I will not give a homework problem or any exam problems on this double film, two film case. So all you have to worry about is the single film case.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.